Lesson 1.3 is on the idea of modeling athletic performance. In this course, the statistical model we will use to analyze an athletic performance is performance equals ability plus random chance. We're going to define each of the three terms in that equation moving forward. When we talk about an athlete's performance, what we're talking about is what an athlete actually did in a finite series of events. For example, if a basketball player shoots free throws in a game and we calculate their shooting percentage, or if a baseball player, we can calculate their batting average for one season, or if we flip a coin 5 times. Each of those are a finite series of events because there's a start and an end. Now, when we talk about an athlete's ability, what we're doing is describing what an athlete would do given an infinite number of opportunities in the same context. And because we are looking at what an athlete would do in an infinite number of chances, ability is essentially an unknown value. For instance, when we're talking about a basketball player's ability to make free throws, if we say that their ability is 60%, that means that we would have to attempt an infinite number of free throws in exactly the same conditions, meaning nothing would ever change, the ball would never lose air, and they would never get tired. And of course, we know that that can't happen. So that's why ability is essentially an unknown value. Now, the third term in that equation is random chance, and this describes the variation between an athlete's performance and his or her ability. For example, if a basketball player has the ability to make 80% of his free throws, but in a particular game he only makes 20%, that doesn't mean that his ability changed for that game. It just means that that was his particular performance for that day. And rather than trying to figure out whether that difference was due to the player just having a bad day or crowd noise or nerves, we just explain it using random chance. Now we're going to look at an example of flipping a coin, and we want to see if your performance matches your ability. Now, if you have a coin at home, you can do these coin tosses on your own. I'm going to use a coin toss simulator during this video, and we're going to toss the coin that way. Anyway, we know that your ability to flip a coin and have it land showing heads is 50%, but we want to see if your performance is also going to be 50%. And we're going to look at a small number of attempts, like 2 and 10 and 25. And then we're also going to look at some larger number of attempts. And if you were doing this in class, you would combine your results with other students. If you're doing it at home, you can toss the coin more times, or maybe have a friend or somebody from your family try some coin tosses as well. So let's pull up this coin toss simulator. And when we start, we're going to just do 2 tosses because the first example in your notes is asking you to toss a coin twice. And over to the side, you can display your results in different ways. So we can do a list, we can do a table, and we can do ratio. So for now, I'm just going to do list. I'm going to click toss them, and we'll see what happens. So it's going to do 2 coin tosses for me, and then it's going to show the results. So notice on this first toss, I actually got 50-50 heads and tails, right? I got one of each, and that's kind of what we expected because that's what our ability is. But we could have just as easily got tails and tails, which would mean 0% heads, or we could have got heads and heads, which would have been 100% heads. But with 2 tosses, we were at 50%. Now I'm going to clear the results, and this time we're going to change the number of tosses to 10. Click toss them. And we'll see what happens this time. So now notice this time, it looks like I have a lot more tails than heads, and I could count those up. There's not a huge number there. It's only 10. But one nice thing about this coin toss simulator is that I can click this ratio button and it will calculate it for me right away. So notice with 10 tosses, I did not get 50-50. I actually only got 2 times of the coin landing showing heads and 8 times landing showing tails. So at 10 tosses, I only was at 20%, which is far below what my ability is. Now we'll clear those and we'll change it to 25 tosses. Now with 25 tosses, I still wasn't at 50%, but I was closer. So notice this time I was at 60% heads, 40% tails. So a little bit closer to my ability. I'll clear the results. And now the directions in your notes say to combine your results with 3 other people in your group. That would make a total of 100 tosses. So let's just do 100 tosses on the simulator. And let's see what we come up with. And notice with 100 tosses, again, I didn't get 50%, which is what I was expecting, but I was even closer. So notice here I'm at 47%. So 47 heads and 53 tails. Now, in the instructions in your notes, it says to combine your results with everyone in your class. So let's suppose that you're in a class with 25 students and everybody does 25 tosses. That would give us a grand total of 625 coin tosses. So let's clear the results. We'll set the number of tosses to 625. Now, the nice thing about the simulator is that you can do lots and lots of coin tosses in a very quick amount of time. So notice here, I am at 51.04% heads. Okay. And if we wanted to, we could do even more and more coin tosses. In fact, let's change this to a really big number. Let's maybe do something like 100,000 coin tosses. So let me clear this. And this isn't in your notes, but we're going to do it just for fun. So there's 100,000 coin tosses, and let's toss them. Oh, I guess that's too big. It doesn't like 100,000. All right, let's try 1,000 then. That's about as big as it's going to go. And notice there, I'm at 50.7%. So what we're noticing is that even though on the very first attempt where we did 2 tosses, we were at exactly 50. But remember, we talked about the fact that you could have just as easily got 0 or 100%. And then our results were kind of all over the place. But the more tosses we did, the closer and closer we actually got to 50%. And that's what we wanted to kind of illustrate here. So hopefully you've been filling in these percentages as we were working through the simulation. And then in part F, it says, in your own words, what do you notice is happening as the total number of flips increases? The percentage of the flips showing heads is getting closer to 50%. In fact, the closest we got outside of the very first one was when we did 1,000 tosses. And there we were at 50.7%, which is very close. And probably if we would have been able to do 100,000, we would have been really, really close. Now, if you were going to graph this, your graph might look something like this, right? We started at the beginning, we were at 50% heads like we expected. After 10 tosses, we were way down here at 20%. And then after 25 tosses, we went back up to 60%. So we were about right there. After 100 tosses, the graph doesn't go out that far, but then we were like at 47%. And a lot of times what happens in graphs like this is you'll see up and down spikes, and then eventually the graph will kind of start to level out, and it's going to get close to 50% as we're doing more and more tosses. This is what's called the law of large numbers. And the law of large numbers is one of the most important ideas of statistics. And what this says is that an athlete's performance will generally get closer and closer to his or her ability as the number of trials increases. Now, we saw this with the coin toss, but it's true in most sports situations. And because we can never know an athlete's true ability, the best we can do is to have them take a large number of attempts or maybe look at data over a large period of time and use that as an estimate of their ability. Another way to look at the law of large numbers is to say that in a small number of attempts, a large variation from an athlete's ability is likely. In a large number of attempts, a large variation is unlikely. Again, think about our coin toss example. If we were tossing 1,000 coins, we would be very, very surprised if we ended up with 90% heads and only 10% tails. However, in a small number of tosses, like 10, that wouldn't be super surprising. In example number 2, it says a baseball player has a career batting average of .200, which is least likely according to the law of large numbers. Now look at your choices. Choice A, B, C, and D are all giving you the number of hits in the total number of at-bats. And one of the things that you might have noticed here is that each of these is essentially equal to 0.8. 4 out of 5 is 0.8, 8 out of 10 is 0.8, and so on. They're all 0.8 or 80%. So the question is, are they all equally likely? Well, what's different about all of these is the number of attempts. The player's batting average is 0.2. So in a large number of attempts, like 1,000 at-bats, we would expect his batting average to be close to 0.2. And D is definitely not close to that, right? That's 80% out of 1,000 at-bats. So that is least likely to occur. 4 out of 5 is 80%, but in a small number of at-bats, it's not super crazy that we would get large variation like that. In number 3, it says that over the course of his career, Kevin Durant made 38.4% of the three-point shots he attempted. Which of these is not likely to happen just by random chance? Again, with random chance, we expect small variation in a large number of trials or large variation in a small number of trials. So choice A says he shoots 35% in the next season. 35% is pretty close to 38, so that wouldn't be unlikely. Letter B says he shoots 80% in the next season, and C says he shoots 80% in the next game. Well, the next game is a small number of attempts. The next season, however, is a large number of attempts, and both of those are pretty far away from 38%. So I would say that probably the least likely to happen is 80% in the next season. Also, if you look at choice D, 0% in the next game is also not very unlikely because, again, a game is a small number of attempts. So, him having a bad performance in one game would not be surprising. Please do assignment 1.3 in your homework packet.